welcome to Pearl Day 2. We have a whole slate of exciting presentations and Q&As and keynotes, so we will get started. The first order of business is going to be Dan Williams' presentation of our kind of update about support for persistent memory in the Linux kernel, and I think he's going to give us a verbal summary. So take it away, Dan.
Thank you for inviting me. Sorry about those technical difficulties. So for this year's update to Perl, I wanted to kind of pick up where we left off from last year, which was at the last year's presentation, we talked about the third rail of Linux file systems, which was an adventure of getting Linux to change its semantics around the fsync system call. That's the primary pillar of data consistency in the file systems. And for persistent memory programming, we needed to be able to do persistence flushing from user space, and needing to do the syscall to do that was entirely too much. So we got that support done. It landed, but then as the dust settled and we looked back, we realized that the DAX facility in Linux, we'd taken some liberties and some shortcuts and turned off some features that were incompatible with DAX. And so as you may know, when you mount a DAX file system in Linux, it throws this scary warning at you. This feature is experimental, use at your own risk, and these kinds of scary warnings. And I wanted to give an update on why that designation is there, what it means, and what's in the way to removing it. The first thing I wanted to clear up is that it's not referring to any known data consistency problems. What it's referring to is the fact that some of these features that we're missing with DAX are pretty deep, and at the time it wasn't clear to developers that we could fix those, add those features without changing semantics, and we didn't want people to be relying on semantics that were going to change. But now it's become clear that we can maintain the semantics, so that's no longer at risk. But we still need to do the work to get the feature supported, and so the experimental tag is remaining until that's done. The big thing that's in the way of experimental removal is the support for a feature called reflink, which is a copy on write technology, so that you can ask the file system to make a copy of a file, but rather than actually transferring data around it, it just makes a new file and refers back to the blocks in the original one, and then uses copy on write techniques to do updates. DAX is an write in place kind of update write in place technology, and so it didn't immediately lend itself to reflink. But we think we have some ideas about what can be done there. The interesting kind of tie-in to reflink that we didn't understand was there until people started looking at it a bit deeper, was that reflink depends on some specific metadata fields and how Linux tracks which pages are mapped to which sections of which files. And while we don't need that mapping for reflink, because those things are used for page cache, and DAX is a technology that turns off the page cache, we do use those fields for error handling. And so in a weird way, in support for reflink, we also have to fix how we do error handling to basically evacuate our use of these fields. And you pull that sweater string a little bit more, and people say, well, hey, if we're going to fix, we're going to be asking the file system to help us do better with error handling, why don't we give the file system even more control of error handling? So that's leading to a project where we want the file system to be to house the list of known errors on the file system. Today, that is managed at a driver level. The driver talks to the hardware and says, "Hey, do you have any known bad blocks?" And I will track that list in my driver, and you can go list those, and you can go you can go ask the file system which physical blocks are related to which parts of this file, and you can kind of manually figure out which files are impacted by errors, but it's pretty manual. And so by moving this into the file system, you could actually do something equivalent to ls errors, and the file system can just spit that out. It could do better free list tracking if it needed to. So those are the major architectural things that we need to change to get experimental removed. But there's also with people's experience with DAX, we've identified some performance caveats that have prompted some people to propose new file systems. There was a new file system from a guy from Red Hat saying, "Oh, I want to do a native PMM file system because I see these problems." But this file system was going after, well, metadata workloads are slow with DAX, and it's interesting because metadata workloads were never a design target of the DAX facility. DAX was all about get a name for a file and then get out of the way and give it to user space programs like PMDK to accelerate. But the criticism still stands. But in response, we're looking at ways to cut out the block layer from metadata updates for DAX file system, so to try to claw some of that performance difference back. The other realization is that DAX makes everything synchronous. So you by the time you submit an IO and submit it, it's done. Basically, we complete the IO in the submission path with a CPU memcopy. And file systems especially like XFS are really built on being able to queue up, have a queue depth, submit some work and go back to doing other things. And so this synchronous behavior messes with some of their performance design. But future systems are looking to have things like the Intel Data Streaming Accelerator, new DMA engines that we can deploy and see if that recovers some of that performance. So just a series of things that of rough edges that we can tie up on the performance side to see how far we can take this DAX experiment on the performance side. How am I doing on time? So in the midst of trying to catch up on some of this backlog, hardware is continuing to advance, and there's new memory related features that have impacts on persistent memory, and we're having to think about what those mean and how those become enabled. Things like memory encryption and memory protection are new technologies that are coming down, and you can see my talk for more deeper description of those CPU technologies. And then lastly, the other thing that's dividing our attention on the kernel side is the fact that a lot of people, the first thing they did when they see this new memory technology is they see the fact that it's just higher capacity, maybe slower performance memory, and they don't really care about the persistence aspect of it. And so PMM is the first, I think, of a series of differentiated memory technologies that are going to be in your platform at once. You're going to have different classes of memory performance that the operating system needs to contend with. And so there's a project called the Memory Tiering Project that's about how can the kernel's existing memory management system be updated, extended to give you all the features you want from your memory management subsystem to perform, like overcommit and balancing access, while also trying to maximize the usage of these resources. That work is starting with a technology called NUMA balancing, which tries to move your memory to your closest NUMA node. And so we're trying to repurpose that facility to move your memory to your closest intended memory performance target, whether it be colder PMEM, hotter DRAM, or other higher bandwidth or lower latency memory technologies. So the effort marches on. There's quite a bit more work to do, and the fun ride continues on kernel enabling for PMEM.
All right, thank you, Dan. So we'll move on to, I guess, Simon, you're doing the quick summary. So
yes.
let me know if you need to advance the slides, and I'll do it for you.
So, hello everyone. My name is Szymon. Together with Igor, we did a talk about C++ persistent containers in PMDK. So it is my short summary of this presentation, just one slide. And so, as you probably know, or maybe you're aware, that the persistent memory programming is not that easy. It's sometimes even counterintuitive. We like to call it paradigm shifting. And it is exactly the reason why PMDK was introduced, Persistent Memory Development Kit. And one of the libraries in this library set is a library called PMOBJ, and it's C++ bindings. And this is, I think, the most powerful and flexible library in PMDK. It contains written from scratch persistent memory allocator. It has transactional API, structures, and like persistent pointer, and so on. And to make persistent memory programming in C++ more idiomatic, we decided to implement persistent memory containers. And they should be considered as a standard library containers counterpart. Currently, in PMOBJ CPP, we have containers listed on this slide. It is array, vector, segment, vector, string, radix tree, concurrent hash map, and concurrent skip list. And segment, vector, and concurrent containers, they do not have standard library counterparts, but their API is very similar to the STL. Radix tree is Radix tree API is very similar to standard library map, with the only exception that Radix tree does not support custom comparator. All of the containers are implemented on top of PMOBJ API. So we are using transactions from PMOBJ. We are using allocator from PMOBJ. And you can check the usage examples in PMOBJ C++ repository. And also in PMKV repository. PMKV is another library from PMDK. It is local key value data store for persistent memory with pluggable engines, and some of available engines are basically associative containers from PMOBJ C++, and but some of them are implemented from scratch in PMKV, and they can also be a good reference, good example of the usage of persistent memory. The reason why we implemented our containers from scratch and we didn't use existing containers from STL because we could implement our own allocator and use it as a template argument for STL containers is basically C++ standard limitations and layout of the structure, because it is guaranteed that in next versions of standard library, the layout won't change. While implementing containers, we faced some performance issue and design choices. The critical pain point, I think, is the number of allocations in data structure. And to limit the number of these allocations, we introduced helper structure called inline string. We also noticed some performance issues related to our fat pointer, persistent pointer, which is an offset pointer, relative to the beginning of the mapping. So we also introduced another smart pointer, a self-relative pointer. And all of that is described in details in our presentation. So I highly encourage you to it, and also our web page, pm.io, and our GitHub repositories. We are planning to implement more containers. We are open for collaboration. The whole project is open source, of course, so any external contribution is more than welcome. And I think that's all from my side. I hope it will be a good starting point for discussion. Thank you.
Great, thanks. Next up is Sasha. Oops.
All right, so the title of my talk was "We replaced SSD with storage class memory, and here's what we learned." Next slide, please. And as many of you know, Optane persistent memory can be packaged in two ways, as a memory module and as an SSD. And so I refer to the former as storage class memory. And my goal was very simple. So I wanted to use Optane as a block device, not in a byte addressable fashion, both as storage class memory and as an SSD. Why did I want to do this? Well, because it is a very simple path for adoption, requiring no changes to application. And I just wanted to see how much mileage we can get from this very simple exercise. And my hypothesis was that SCM would be faster. After all, it sits on the memory bus and produces higher bandwidth and lower latency than SSD. But this is not what I found. Yes, next slide, please. So this chart, it's a bit difficult to read, but bear with me, I'll explain what it shows. It summarizes our experimental results with MongoDB storage engine WireTiger. Y-axis shows the names of workloads in our benchmark suite, and the x-axis shows throughput in operations per second. So the further to the right we are, the better. And red and yellow bars show storage class memory with either one or two modules. That's as much as I had on my experimental system. And the blue bars show the SSD. So the key point here is that storage class memory was not faster. Let's go to the next slide. Yeah, so why was that the case? There were a number of factors that came into play. In micro benchmarks, Optane storage class memory delivered about a 5 times higher throughput than an equivalent Optane SSD. And you could go even higher if you used more Optane modules. But the write throughput was very low. And what was even worse is that write throughput scales negatively if you use multiple threads. So that's not just my conclusion. Others in research groups, and including Steve Swanson's group, observed that as well. So the good news is that the latency of reading from storage class memory is about 100 times slower than reading from the SSD. Yeah, we're still on that slide. So, but our benchmarks are throughput oriented, and we use the block storage API, so they did not enjoy the benefit of lower latency. The main reason why SCM wasn't faster for us was DRAM caching. So the throughput of storage class memory is still 5 to 10 times lower than that of DRAM, which is not a bad thing. It's great to be only 5 to 10 times lower than DRAM for a storage device. But if your workload can benefit from DRAM caching, it'll still be much faster than going directly to storage. And so in my experimental setup, WireTiger made a really good use of DRAM caches, both AOS buffer cache and its own internal cache. So the benefits of having a better read throughput on storage class memory didn't make much difference. And in fact, Dan Williams mentioned both of these factors, DRAM caching and SSD sometimes delivering better throughput than SCM in his talk as well. Next slide. So does this mean that Optane persistent memory is never a good replacement for storage? Well, not at all. So in my talk, I described you a single data point. It was just one experiment. So it could very well be a good replacement for storage device in DRAM constrained environments. So for terabyte size workloads, mine were only hundreds of gigabytes in size. But the main insight from my experiment is that adopting persistent memory in a storage system requires some careful thought. It can't be simply used as a drop-in replacement for your storage device. And write throughput remains the Achilles heel of this technology. So Optane will really shine when we use it in latency-sensitive workloads that can't benefit from DRAM caches. And the final slide, please. Oh, I guess it's not there. Well, if you want to know about more details of the experiment, they're written up in my blog post, and you can look it up by searching on my by finding my website, and I believe it's linked there. Okay, over and out.
Sorry, I missed one of your slides, Sasha. I'll get it back up here at the end.
No worries.
All right, up next we have where are we? We have I believe Haris is going to talk. Take it away. You're muted.
Can you hear me now?
Yep.
Okay. Good evening, good morning. Thank you for the invite. So what I will present today is joint work with Terence Kelly. Next slide, please. Preserving application data integrity is a paramount duty of computing systems. As we all know, failures such as power outages are major perils. A sudden crash during an update may corrupt data or effectively destroy it by corrupting metadata. Applications protect data integrity by using update mechanisms that are atomic with respect to failure. Such mechanisms promise to restore data to a consistent state following a crash. Unfortunately, the checkered history of failure atomic update mechanisms precludes blind trust. Widely used relational databases and key value stores often fail to uphold their transactional guarantees. And lower on the stack, durable storage devices may corrupt or destroy data when power is lost. How about persistent memory? Emerging non-volatile memory hardware and corresponding failure atomic update mechanisms strive to avoid repeating the mistakes of earlier technologies, as persistent memory for conventional hardware. However, healthy skepticism demands first-hand evidence that such systems deliver on their integrity promises. We believe that prudent developers should follow the maxim, train as you'll fight. Basically, they should subject their entire hardware-software stack to the failures that it must tolerate in production. So along these lines, we developed a cheap yet effective power failure testbed to subject applications running on a complete hardware-software stack against the whole system power interruptions. Next slide, please. So here is the basic idea of our power fail testbed. The host computer on the right is a single board computer, such as a Raspberry Pi, and it's the only computer in the picture. Persistent application data lives in a USB-attached storage device hanging from the host, and the host can cut its own power by sending a signal via its general purpose input-output pins, which are available on the Pi, to the power interruption circuit in the center. So the heart of the power interruption circuit is a tiny electromechanical relay, and power from the power supply on the left runs through the relay's normally closed contacts until the interruption circuit cuts power by switching the relay's poles back to the normally open context. Next slide, please. And here you can see a complete prototype testbed on an 8.5 by 11-inch sheet of graph paper, which we call Pi nap because it causes our Pi to take a little nap. So from left to right, we can see the wall-wall power supply, the power interaction circuit in the middle, and the Raspberry Pi Model 3B Plus with a USB thumb drive attached. So everything shown here costs well under $100 and can be built in a few hours. The testbed can run unattended indefinitely and performs a full power off on test cycle in 1 minute. And next slide, please. So we use our testbed to powerfully test the recent user space library implementation that Terence implemented for persistent memory called Famous NAP, which targets conventional computers with ordinary DRAM and block storage. The library provides a crash-tolerant mechanism, which is called failure atomic MSync, that lets programmers commit changes to a memory map file atomically to protect data from crashes. Now, to test whether the famous NAP implementation of failure atomic MSync protects application data from power failures, we wrote a very simple test application. And the test application repeatedly fills memory with a very specific pseudo-random pattern and calls failure atomic MSync. So as the program is running, we cut and restore power with PiNap and check whether the backing file containing the persistent data has the expected pseudo-random pattern. So in over 58,000 tests, the famous SNAP implementation passed over all the test, which to us suggests that it's not completely broken, but we cannot preclude that there is no bug. It's just like past 58,000 power failure tests. So to wrap up, our key message is that software developers should use this testbed or something like it to evaluate perfectly crash tolerant software before releasing it for production use. And that's all I have from my side.
All right. Thank you, Haris. That was our last summary talk. So we will turn it over to questions. I've been tracking the ones that have come by in the chat, so I'll ask some of those. But if I would encourage people also to raise your hand to ask your question, even if you already typed it in chat, and we'll have a few more voices. So go ahead, Sasha.
Yeah, I have a question to Dan Williams. Dan, it might be a dumb question, but do you know what the difference is between direct I/O and DAX?
Yeah, so direct I/O is asking the kernel to try to suppress cache effects, and DAX is the page cache doesn't exist. So
which
in the case of direct
I/O,
they sound very similar. The direct I/O is a compliant implementation of direct I/O is actually a file system could cache it in DRAM and then write it back out immediately, and it would still meet the semantics of direct I/O. So there's optimized file systems do bypass the page cache, but there's lots of corner cases, and semantically it's not guaranteed. Whereas DAX is saying there's no page cache in behind mmap mappings. They're going straight to storage.
And do you know what the difference is in DAX implementations between ext4 and XFS?
They both use the same core. There's a file system, the fs/dax.c, which both of them use. So in terms of the mechanisms of mapping pages and all that, that's all shared code. The differences, the main differences between them come down to how they update metadata, and ext4 actually uses the page cache for its metadata updates, and XFS does something different. And yeah, they're not their differences are based in their historical differences, not their DAX implementation. On the DAX front, they're pretty much identical.
Thank you.
Itzhak Burke, go ahead.
Okay, I have a question to Sasha. In the results you presented, SSD as a block device versus persistent memory as a block device. Did you try using DRAM as a block device, just as a sanity check to make sure that the issue is not interface overhead as opposed to anything else? Would be interesting to see DRAM.
I have tried to use DRAM in my early testing. I have not run the whole battery of experiments on DRAM. So I'm pretty confident that interface is not the issue here. So I ran a bunch of micro benchmarks and they're all on my blog. And what I basically show is that we have, so when we use, so in my experiments, I use both, I access PMEM as a DAX device, and I also accessed it via ext4 DAX, and I used mmap. And so I showed that in micro benchmarks, there is no overhead of using this, file systems, because so we're able to achieve the theoretical device throughput, even though when we use these access methods. So I don't think it's the interface issue. In general, my observation is that using ext4 DAX over persistent memory does not add overhead for as long as you don't do anything, metadata heavy. If you just, do reads and writes, it does not introduce overhead. So I don't think it's so much the interface issue. And so the limitations of, for example, limited write throughput, not scaling, I saw that, without in micro benchmarks where, software stack was not in a way. So yeah, I don't think it's
okay, thank you.
Adam Manzanares, go ahead.
So I have a question, two questions for Dan. One is you mentioned using NUMA balancing to alleviate some of the performance difference between DRAM and PMEM. But what I understand in NUMA balancing, you find a target page and then swap them. And so do you think that that's a good approach with the performance difference between PMEM and DRAM? And is there any way around that, or is there anything you guys are working on to alleviate this?
Yeah, well, so the NUMA balancing is trying to proactively move things, because there's two sides to the placement problem. There's aging the memory, and then there's like fixing it up after the fact. So you kind of alluded to it. For the aging problem, we're trying to see what we can do with migration we're calling it migration in lieu of discard. So we have all the normal memory pressure things to push cold pages out to swap, and we just inject PMEM as another tier in that path, so that the migration we're doing in response to page reclaim is actually pushing cold pages out to PMEM. But yeah, in terms of the algorithms for like identifying the hot pages and moving them back, that's the harder part of the problem. And NUMA balancing kind of gets there, but yeah, we're still searching for a better way to do hot data tracking.
Okay, and the second question I had was with the DSA being introduced, doesn't the IOAT DMA engine already have some of the features you would need to offload the CPU, or like is there anything wrong with it, or why move to the DSA?
It did, and we had hopes, and we tried it, and it didn't work. I think it's just an architectural issue with the way the engine is there in the sense that it requires you to write these large descriptors. You have to go touch MMIO space, and the amount of work to launch a a 4K transfer is on the order of the amount of work it is to just do it with the CPU. CPU memcopy on Xeon is just that fast, so it's hard to keep up with that. They specifically went after those kind of problems with DSA. The submission path is just an instruction. We have this new instruction called movedir64b that lets us submit work more efficiently. So no promises, but the design is meant to make work submission much cheaper. I think they also do some things on the back end to, whereas like I think IOAT tended to behave like a single core in terms of bandwidth, and DSA can tend to behave like the entire package in terms of consuming more bandwidth. So we'll see if that gets us to finally be faster than CPU memcopy.
All right, thanks a lot.
Great. I have a question for Igor and Szymon. So when you set off to build these new containers, is there some deep reason why you didn't implement the same data structures that the STL provides, and why you went off and chose some different structures to implement?
So if we're talking about the internal structure behind, for example, our associative container, so in case of container which will resemble stdmap, we choose to implement radix tree because we found out that radix tree has some nice properties for persistent memory. For example, there is no rebalancing, which is quite costly on PMM because for rebalancing we would have to make sure this operation is consistent, so we would have to use transactions. And there are some papers, for example, which compared performance of red-black trees on persistent memory, and it was not so good. For some other data structures, we also take some existing implementations, for example, from TBB. So both concurrent hash map and concurrent map are inspired on TBB. I think in our future containers, we will also try to just do some research and find out which structures are actually the best fit for persistent memory.
And I can give you one more example. We have a container segment vector, and it is basically a vector of vectors. And why we do not end up with implementing only the vector? Because of the limitation of the allocator in LPM OBJ. We have a limitation for the maximum allocation size, and this is due to the design of the allocator. And it is also related to the problem of the fragmentation. So it can be another reason why we do not copy one-to-one the algorithms and structural layouts from STL.
Great. Jan, do you want to go ahead and ask your question?
Sure. So I tried to use the containers in PMDK, and I noticed that some of these containers can be used within transactions, while other cannot be used within transactions. So basically, you can use a vector inside, but you can't do the same with a map. So this is probably some design choice, but why is this design choice there? Because as a user, I wish to have several data modified within a transactions, some residing on a map, some on a vector. And like, are you going to change this or provide new containers that will let me put a hash map inside a transaction?
Yeah, so actually the problem with calling some methods within a transaction, it is mainly for our concurrent data structures, and it is connected basically to our internal implementation. So for example, in some cases, we need to do some work within this method to, and this work must be transactional, and we have to guarantee that this work will end inside this method. So we basically have to commit this transaction within this method. But in our current design of PMDK transactions, if we have two nested transactions, then they are flattened out, right? So the commit is actually done only when the outer transaction commits. And this means that in case of concurrent operations, we basically we cannot delay some changes to the end of the outer transaction. We have to do them in some special order within our methods. So for all our single-threaded structures, the operations can be used within a transaction. And as for concurrent ones, we have some solution in mind. So we were thinking about exposing some way of creating independent transactions so that you can just use that as an implementation detail. And then all of other work can be just used in a user-provided transaction. So I'm not sure when we do that, but and if that will work for all our data structures. So we will probably need to think about the design, but I think for some of them we will try to make it possible. Yeah.
And yes, like Igor said, it is only the case when with concurrent containers. Your question is very good, and we was thinking about that while we were designing our first containers, single-threaded ones. And if you want to use a single-threaded map, you can use radix tree, and you can easily combine methods from radix tree and vector inside the same transaction.
Yeah, and for some single-threaded hash map, I think we will also try to implement something in the future, because concurrent map, while it has a pretty good scalability, it has some overhead in a single threaded workload.
Thank you. Maybe one quick question more about self-relative pointers. Can you use them with pmempool set or only with a single pmempool file?
Yes, you can use them with pool set, because underneath, even if the pool is consists of multiple files, they are all mapped next to each other. So the address space is contiguous, so there is no problem with that. Yeah, as long as it's the same pool, of course. You can have cross-pool references with the self pointer.
All right, we have a question for Haris. Your test approach works well for physical systems. Do you have some ideas on how to test power failure when working in the cloud or doing remote development?
Yeah, that's a good point. From our experience is that when we try in the past to use like servers or workstations, our experience is that there is no straightforward facility to force a sudden power interruption in a server. So we don't expect to have such features in the cloud. And one way would be to try to do like something like a soft reboot. The problem with a soft reboot is that you don't really pull the rug under the application. So I think if we really want to, if we collectively believe that we need to stress test our applications for power interruptions, and we want to support something like this in the cloud, that might be something that the vendors will have to support in like providing a power interruption circuit that you can use through a library to interrupt your application. Otherwise, I don't think the existing servers provide such facility. And the reason they don't provide is that usually you don't want to cause any damage to the server. So maybe that's something that the vendors will have to decide that, you know, I can provide a pool of servers just for the whole purpose of doing power testing and yeah.
All right. Sasha, do you want to ask your question?
Yeah, so I have a question for Igor and Szymon. So my question is about what is the use case for persistent containers, not just containers that you implemented, but in general. So let me explain where I'm coming from. I'm going to be a little mean just to sort of illustrate my question. I will try to be a little bit of a devil's advocate. So it seems to me that if I have a data structure and I want to make it persistent, and at the same time I want to get good performance, so if I just use any kind of persistent containers, it seems to me that I'll just get slow performance right away because, well, very often you have to access persistent memory as opposed to DRAM and flashed operations to maintain asset properties. And so in light of that, it seems to me that I would, if I wanted to have a persistent data structure, that I would just go and use a key value store with asset transactions because, there is 30 or 40 years of wisdom of database research, and these folks rely on DRAM caches and fast logging to give me the illusion of DRAM performance, but actually maintain persistence. So if you could, but you perhaps know more about how people use persistent containers and who your customers are. So if you could shed some light on that, that would be really great. I hope that makes sense, my question.
Yeah, so, well, I think there can be several usages. So one of them is that we can use basically libpmobcpp along with its containers in a pretty general purpose application. So we can just mix, we can just have persistency in a normal application, which does not maybe need a full-fledged database. So one example of that is, I do not remember the name exactly right now, but there is a project that tries to implement some framework on top of libpmobcpp where we can just implement some server-side logic based on libpmobcpp. And I think with this, we can, for example, get rid of some translation layer between database and application, right? We don't need something like Hibernate, all those mapping layers, which is often very cumbersome to implement and also have some performance penalties. Of course, it depends on the use case. So this will not be the case for all applications, but I believe it can benefit some of them. And other usage is what we also seen a few times is storing, for example, some metadata along with other mechanisms. So we still have some database, which is based, for example, on SSD. And on PMM, we want to store some metadata, some information about these blocks on SSD. And we want to have also fast startup of this data. We don't want to load them from SSD to memory on restart, but we just want to keep them just to have a fast look, right? And in those cases, maybe we can pay some cost for performance degradation for example, inserts and reads. I'm not sure if Szymon wants to add something else.
Yes, I can confirm that mainly in these usages, but the general idea is to make programming persistent memory in C++ easier. And the great example of that, of the usage, could be implementation of our engines in PMKV. So like you mentioned, we have key value data stores. And you can implement with these containers quite efficient engine, relatively simple, using these containers. I think a good example is S3 engine in PMKV. Correct me, Igor, if I'm wrong. But I think we are using containers over there.
Thanks.
I have a question for Dan. So you said that there doesn't seem to be a strong case at the moment for a PMEM specific file system. I'm curious if you see a need either now or maybe potentially, or an opening for a new kind of file system to rule them all that is built for PMEM and SSDs and disk that would serve all those purposes kind of equally well? Or do you think that evolving XFS and ext4 and ButterFS and so forth are going to get us to a place where we can just use one file system or a few file systems everywhere and have them work pretty well?
Yeah, I made that slide and I'm like, this is kind of controversial. I was going to do it anyway because maybe it'll get some questions asked. But I put that in there more to kind of challenge the new file systems to go after something other than, like, the presentation I've seen of new file systems. They start off with DAX metadata workloads are terrible. And it's not clear that people are moving to persistent memory to run file system metadata workloads. But they are challenging the implementation to do better. And so what I'd like to see is once some of these major performance caveats that we've identified have been resolved, then where are the fundamental gaps that a new file system might fill? As long as we still have to do bulk storage and bulk I/O, I still think that that NVMe SSDs are going to be like the major consumer of the file system. And until PMEM can be a direct replacement for either your direct write-in-place workload or your bulk storage, I think we're going to be having this evolving the existing file systems versus replacing them.
All right, thanks. I have a question from the chat for Sasha. The Optane SSD you used in your comparison has a pretty big cache. Do you think that reworking the Optane DCPM SSD driver would benefit from adding a DRAM cache ahead of memory?
I think Jim asked this question. Jim, could you clarify, do you mean about adding a cache to the storage class memory package, or what do you mean exactly by that, head of memory?
It was more the standard Optane SSD products from Intel, like I believe the X10, have a pretty large read and write cache on the drive themselves. Yeah. At least from your test, what it looked like was probably the poor write performance could have been that the SSD driver that you were using for the Optane memory modules doesn't have a DRAM cache or has a very small one. Is that something that you would suggest would potentially benefit and might change some of the results of your testing?
Oh, absolutely. I also think that, so I think I hypothesized that there are a couple of reasons why the write performance is worse, the write throughput was worse. One reason is because is probably because SSD has a large DRAM cache, and another reason is probably because there is just more parallelism in the SSD because there's just more memory chips. And if I think Andy Rudolph is here, so please jump in and let me know if I'm talking nonsense. But and yes, of course, I believe that adding a write cache that can be whose contents can be made persistent on power failure will of course make write throughput of persistent memory better. The question is whether it can be added, easily in the form factor provided and still maintaining the cost envelope and power envelope. And I don't know that.
Okay, thank you.
And I have to go teach, so I'm going to sign off.
Thanks, Sasha.
Bye.
Let's see, I think we have time for probably one more question. So this is another question for Dan. Are these features that we're seeing coming into Linux, do you expect those to show up in Windows as well, or is that out of your hands?
That is definitely out of my hands.
Are they? Do you know if they're working on supporting the same kinds of things, or?
we all see the same. We all seem to see the same CPU roadmaps, but statements about what Windows is going to do usually come from Microsoft. Yeah, that's about all I can say.
I asked the question, and I was just waxing philosophical. One of the advantages of the existing model that was driven for persistent memory is that the verbiage is very similar between Windows and Linux. But a lot of the work that you're doing is specific to Linux in terms of some of the file system work or some of the other additions. I think it was more just philosophically, would we as a body hope that Windows and Linux continue to match similar features so that it's easier for app developers to deliver a product?
I mean, I will say that historically, even if Windows hasn't picked up on a hardware feature, when Linux does, it tends to create movement. So yeah, I would expect parity, but I have no specific knowledge that I can share.
All right. So we are basically out of time. Thank you all for your questions. Before we move on to the keynotes, I wanted to do one quick order of business. I would like to try to take a group photo. So if you're willing, if you could enable your video, and I will just grab a screen capture. And this, this photo may be published, probably not too widely if we're realistic about it, but it'll go up on the internet. So turning on your video is, I guess, your implicit consent for that. And if we can get up to, I think it's 30 that we can pack on the screen at one time, then that would be awesome. Dan, your video is black. Can you mute your video if you don't want to show up? And then we don't have a black spot in our group photo. Or I'll fix it in post. All right. All right, everybody smile. Say Pearl. All right, thank you very much.